Hi, welcome to the Signal Path. As promised on Patreon, we're going to take a look at more and more interesting and unusual microwave devices. Please do check the Patreon page if you're interested in contributing to this cause. So here we have the OPTOELECTRONICS APS104 4 MHz active bandpass filter, which I came across while I was browsing eBay, and quite a few people were interested in it, so I had to bid a lot in order to get it. So it's a little bit unusual. I didn't even know that such a device existed. So this is a 4 MHz active bandpass filter between 20 MHz and 1 GHz. So essentially you can tune that 4 MHz anywhere between these two frequency extreme ranges. Now this becomes quite difficult at very high frequencies because 4 MHz becomes a very small fractional bandwidth as you go towards the 1 GHz, therefore representing a very high quality filtering to be achieved. Now there are many ways to make a tunable bandpass filter, and I'll show you a couple of examples of it in just a second. But it does have two ports, two BNC ports over here in the front. It does have a kind of an interesting mechanism. This keeps turning and turning and turning, so there's clearly a potentiometer in there. And there's an LED in here, and if I turn it on, that LED briefly turns on, and it just turns back off. So it clearly has some battery in it that's probably mostly drained. The screws that you see are missing over here. I actually removed the screws because I lost the shot that I took initially to introduction. I haven't opened it yet. That's why the screws are not, but it did come with it. So it's supposed to be working. It does have an 18-volt input on it as well. So I'm curious to take a look and see how they built this, and we can reverse engineer and also do some measurements on it and figure out if this is good for kind of applications we're looking for. And here's the inside of the unit. A little bit surprising there's no silk screen on this PCB, and the cables that are coming to this potentiometer have no shrink tube, so it's actually almost falling off. So I'm going to have to fix that later on to make sure that it is going to stay on quite nicely. There's a battery pack, so it clearly does have a battery in there. So we're going to have to reverse engineer this a little bit, figure out how it works. I see a very large Wilkinson power divider here in the middle of this. But yeah, I think this thing should slide out. Yep, it does. So let me open it a little bit more so we can take a closer look. So this is indeed very unusual. There's no way they built this in large volume. It must be something that they just essentially built to order. So the battery is broken up into multiple parts. And I did notice that the negative cable of the battery was actually trapped and screwed over on top into one of these channels here on this. Really quite rough actually. So this connector here was the front panel. I disconnected it, and on the other side we see the other parts. So I have some rough idea of how they could have potentially built this. I'll take a look at the battery and see what kind of battery it is, but I'm inclined to not even include the battery in it. I mean, you can just run it from external voltage. I don't really need the battery, and it's probably not very good anyway. But let me describe to you how this works. So I went ahead and repaired this unit. The repair itself wasn't very exciting. I'll explain to you what I did, but I think it's a good opportunity to turn this video into a tutorial instead and talk about tunable bandpass filters or even band reject filters. How do you make them? What are the different pros and cons of various architectures that are used? I have a whole bunch of different examples here which we can go through and then ultimately work our way up to the design of this one that has some unique features that makes this design interesting, I think, for exploration, especially from an RF point of view. We'll talk about these disadvantages as well. So I fixed these cables, so that's nothing unusual, but then I noticed that you couldn't charge the battery on this. So it does have a little port over here which you can apply 18 volts to it, and when I did that, nothing happened. I removed the battery because there's no point really. Anyway, the battery used to be connected over here. The circuit they used to charge the battery is really simple. So all they were doing is that they were taking the voltage from the external source here, passing it through this voltage regulator. This voltage regulator has a diode connection into the battery. So they were just setting this voltage to the maximum voltage of the battery and essentially trickle charging it like that. Nothing sophisticated, but I guess it works. When you remove the battery, the voltage regulator would put a constant voltage here, and this unit can actually only run from the voltage applied here. And that's why that it wasn't working. That's probably how it ended up on eBay, because they couldn't charge the battery anymore. The voltage regulator was dead. And here's the replacement, by the way. You can see I took it out. And the reason voltage regulator had died was because this tantalum capacitor over here had become a short circuit. So I had to replace that as well, which is this one over here. So this tantalum became a short circuit, which shorted the output of the regulator, and eventually that killed the regulator. There's a potentiometer over here, which allows you to adjust the value of that. So this is set to just essentially 15 volts. There's a lot of other circuits here, which I will explain. But before we go into the architecture of this, let's talk about bandpass filters, and then we can go back to this. And there's a lot of cool measurements that I want to do with this one to show you how it works. There are many different filter architectures, and there are variations within every architecture. You can write many books about that alone, and people have. We're going to talk about tunable filters and see how we can make a couple of different examples, particularly filters that have a fairly high quality factor, so we can get some really narrow band and potentially with very little loss. So I have two mechanically tunable filters over here. This is a bandpass filter, and this is obviously a band reject filter. And essentially, all you have to do is turn one knob, and this knob carries the frequency. You can see this one goes from 1 gigahertz to 2 gigahertz. So it only changes by a factor of 2. That gives you an idea of how hard it must have been to design a filter that goes from 20 megahertz to a gigahertz if they were going to use the similar architecture of this one. I would say it may even be impossible because of the huge range in frequency. So the architecture of these guys must be very, very different. And this one is a band reject. You can see this goes from, I think, 250 megahertz, not even less than that, 200 megahertz all the way to, what does it go? I forgot what it is now, 400 megahertz. So even that one is really not even a factor of 2. But these guys have very high quality factor, and they do have one advantage. They have no DC power consumption. They're purely passive. They're fairly large. You can see, quite large, especially this one. So they do take a lot of area, and even though that filter goes down to 20 megahertz, it is a fraction of the size of this one in reality, because the architecture is very different. So what do these look like on the inside? I'll take the lid off and take a look. It looks so cool on the inside, and as always with these different microwave components, the inside of these look really non-intuitive because we're not used to thinking about EM propagation in different cavities and modes of propagation through different slits and so on. But of course, this is why this is almost like magic. And let's not lose the awe of the fact that people figured this stuff out at some point in history, that we managed to figure out how to manipulate these waves that we didn't even know existed. Really, always quite amazing. So first, let's establish that one of the easiest things to tune is a capacitor, because you can always move either a dielectric or a conductor between two plates, and depending on the overlap region, you can change the capacitance. This is how most mechanically tunable capacitors are actually made. And we'll talk about solid state ones later on. So when I turn this, you can see that the entire structure turns at the same time. We have a belt drive over here, and this belt drive does nothing more than just translating the ratio, so the rate in which these things turn will be a little bit different. But in the corners, somebody has bent all these fins in a different shape, and if you look, the little piece of metal in the middle has a unique shape. So as you rotate, eventually at some point, you get an overlap to that center piece here. These two fins here, you get an overlap, and then in some places, you get an overlap. So that's obviously a tunable capacitor. Now, this is a fully reciprocal network. That's one of the advantages of these passive filters. So either of these can be thought about as input and output. But you come over here, and you're still in coax mode, and you come out, and then you tap into one of the metals of this pin here. So these are obviously tunable capacitors, as we said. Now, everything here matters. The shape, the location, everything matters. So this pin, even depending on where you couple it to this line, will affect the filter characteristic. Now, as you turn this, you're changing that capacitance. Now, these chambers, or these tuned resonant cavities, actually talk to each other because there's holes there. Those holes may operate in some kind of an evanescent mode and couple these different cavities together. So this gives you 4 different chambers. So you have 4 elements that are tunable, that you only tune the capacitance of, because every other dimension is fixed. You can't change the size of the cavity. You don't change the size of that hole, which changes the coupling factor between the cavities. And all the inductive or the equivalent inductive behavior, because of the coupling, is all fixed. So you're only tuning one thing. And that has some consequences to what happens to this filter. And as a result, this filter's bandwidth is inherently behaving very different than the one we are going to take a look at the very end. This thing is not going to have a constant bandwidth. It's going to have a constant fractional bandwidth, meaning that the bandwidth of this filter continues to increase in absolute sense as you go to a higher frequency, because it has a constant fractional bandwidth. That's a big disadvantage. The other filter that we're looking at has a constant 4 megahertz bandwidth, so it's fundamentally different from this. Now, you could make a mechanically tunable filter that has a constant bandwidth too, but you can't change only one thing. You can't change only the capacitance. You're going to have to change the coupling factors. You might have to change the size of these holes. You might have to change the size of these cavities, and everything has to move at the same time. A very difficult mechanical problem. So it's typically not how it's done. And these individual fins here are designed with slits in them, so you can bend them out of way, so you can tune the capacitance a little bit differently between all of these 4 stages, because these 2 corner edges at the end have no capacitance, and there's no coupling to the outside of this. They have coupling to the center only, but the center pieces have coupling to both sides. So that changes the value of the capacitances that you need to achieve. That's why these corner ones are tuned a little bit different. Again, this is a very complex EM problem in reality, and you can model and simulate that. And I'm not getting into the details, perhaps not doing it completely justice, but you'd have to dig into it a lot more. Hopefully this gives you a pointer to go and look at it. But it looks to me like just simple coupled resonant blocks there where you can tune with a capacitor. Now, this is again going to be completely different than the one that's a band reject. Let me bring the band reject one here. Here's our band reject one. So it shares one thing in common, And that's the fact that, well, it still uses a tunable capacitor as the component that you can adjust. Again, because it's the easiest thing to do. But there are no holes in here. So these are not coupled together. And that's because you have LC, LC, LC resonance components here which become a short circuit. And once you short circuit them, that's a band reject filter. So you get the signal coming through over here, and then you pass it to the next one, you pass it to the next one through these coaxial connections in between, and then you have an L which is wrapped around and a C, and it looks like that's how they do it. They have a series L and a C which becomes a short circuit at a particular frequency. L's are fixed, C is tunable. There you go, that's how you do band reject, and he has 3 cavities here. And if you look over here, there's a cable that comes out and then wraps around, connects to this one, wraps around, connects to that one, so you have 3 of them in series, and it looks like there are tiny little individual varactors here, which they're probably using to fine-tune the value of these so you can align those LCs so that they can be exactly on top of each other, so you can get a higher order band reject filter using this structure. Again, fundamentally different actually the way this operates than the other one. That's why again there are no holes here. So these do not talk to each other at all in evanescent mode or anything. They're in series with these coaxial connections in between them. So let's measure these so we can see the observe the behavior. Maybe not this one, just the band pass one, because that's the one we're comparing with the other filter we're looking at. But hopefully this gives you some idea of how they built these ones. So let's go ahead now and measure our WaveTech tunable bandpass filter. So see its characteristics, and there's a lot we can learn by looking at S parameters. For that, I'll be using a Keysight E5071C. This is a 20 gigahertz version. We don't obviously need the full range, but let's take a look and see how it behaves. And here we can see the complete 2-port S parameters. And right away you can see that S11 and S22 are symmetric, and S12 and S21 are symmetric. As we said, this is a fully reciprocal block, so therefore it's going to behave this way. We can also see that we are right now set to roughly in the middle of the band. Right now I'm at 1.5 gigahertz. If I move the filter left and right, you can see that all of these 4 graphs move at the same time, and that's also to be expected. Now we can make some additional observation. For example, we can note that the S11 and S22 of this system are only matched to 50 ohms right where the filter is in its band pass mode. And if you think about it, that makes sense, because the way this filter actually does band pass filtering is that outside of its center frequency, it reflects everything back onto the ports. So that's how the filtering actually happens. It doesn't absorb any of the energy you put into it. It reflects it when it's outside of its bandpass filter and passes it through when it is within its bandpass filter. And that means that the impedance of this filter outside of the center frequency are really bad. They're fully reflective. So if you have a broadband amplifier connected to a filter like this, it's going to see a wide range of impedances inside and outside of the bandpass filter frequency. And that is, of course, an inherent disadvantage of a filter like this because of its poor impedance portfolio across its tuning range. But we're going to have to live with that. This is, of course, passive after all and reflective. Now, if you look at the center here, the insertion loss of this filter is reasonably good. It's about a dB and a half here, right in the middle of the band. And that is, again, because this is a big, bulky microwave component, and it's going to have a very high quality factor cavities, and so its insertion loss is not too terrible, even though it has 4 stages. Now, the other thing is to do with its bandwidth that we talked a little bit about earlier. Let's tune it all the way down to 1 gigahertz center frequency. There you go. You can see that the instrument is marking here the 3 dB bandwidth of this filter. It's about 44 megahertz at 1 gigahertz center. Let's move it all the way now to the 2 gigahertz center. And now you can see the filter bandwidth has now more than doubled. It's about 98 megahertz. And that's in line with what we were saying. This filter does not have a constant bandwidth, but rather has roughly a constant fractional bandwidth. To make it a constant bandwidth, it's going to be very difficult using mechanical means only. So this is not going to do what we want, and the instrument that we're going to take a look at is inherently different. So what else we can do? Well, we can make a YIG-tuned filter. Now, I did a full video on this, and I've done a couple of videos on YIGs, so I won't get too much into this. But you can watch this video where I turn this automatic pre-selector into one that I can adjust manually, and I added an LCD screen over here so we can track the frequency. But to make the story short, this is basically a YIG filter based on a material whose dielectric constant changes as a function of magnetic flux. So there's a very strong electromagnet that tunes a YIG filter. Now you can get extremely broad frequency range from this, and this is why YIG filters are used as pre-selectors in front of spectrum analyzers. But YIGs are expensive, bulky, and very power hungry, and are difficult to make at very low frequencies. So to make a YIG filter from 20 megahertz to 1 gigahertz would still be a very big challenge. So it cannot be done this way. So as a result, we're not going to use this technique neither, which means that that instrument is again different from how this one works. And again, go and look at this video if you want to understand exactly how this works. But Yigs is another option, just not the one we're looking for. So how about a filter that is tunable using solid state waves and is very compact? So here's an example of one. This is actually 3 filters on top of each other. This is from an old publication from Bell Labs. I borrowed this from one of my colleagues. And this is 3 filters on PCB where they're merged together by stacking 3 PCBs on top of each other and essentially gluing them together. So they have to be co-designed in some way because the dielectrics of these different materials will interact with each other. So here's the input and output of the first filter at the very bottom. Here's the input and output of the second one, and the input and output of the very top one. And the top one you can see the traces very well because there's nothing above it anymore. If you look carefully, these little tiny black components, those are actually diodes used as varactors. By adjusting the value of the capacitance of these varactors, you can tune the center frequency of these filters. But these filters essentially behave very similarly to our microwave filter in terms of their characteristic of the input and output impedances. They too also have reflective behavior outside of their frequency range, and they also have a constant fractional bandwidth and not constant bandwidth response. I'll put some of those plots on top of this video as you're watching it so you can see how this was put together. You can go and read the paper, of course. This also has another minor disadvantage, is that these varactors have a certain linearity limit. If you put too much power into it, you run into the nonlinearity of the diodes and you introduce nonlinearity in your filter overall. So that's another disadvantage, but you get that for compactness. This thing burns no DC power. The varactors have essentially no DC power consumption neither, but it has some price to pay. And its insertion loss is going to be a little bit more, but this is actually surprisingly good, as you can find out in the paper. So yeah, that's it. That's another example. So, but this is still not what we're looking for, because it does not give us the constant bandwidth. And finally, here we are on our mystery filter. Now, there is another category of filters I didn't talk about, which are pure semiconductor-based solid-state filter using GM cells and various on-chip capacitors and feedback networks and so on and on. I didn't talk about that because that's a whole other category in itself, and a lot of people, in fact, build filters like that. And the advantage is obvious because it's fully semiconductor-based and it can be extremely small. But putting that aside, this one can actually be built entirely in a semiconductor material except for the center frequency filter over here, and we will see why that is. So here's the input and here's the output. You can see the output has some additional shielding, the input does not, and we'll talk about why that is in a second. So the input has a frequency content anywhere from 20 megahertz to 1 gigahertz. If I flip on the other side, you can see what they do with the input. The input comes over here, goes through some matching network, and it hits an amplifier. So right off the bat, this is an active filter because they're doing some amplification. So this thing can actually have gain. It doesn't even have to have loss, and because of the amplifiers that are embedded. Another property right off the bat is that because this input goes into an active device and has a matching network, the input of this filter is matched across the entire frequency range from 20 megahertz to 1 gigahertz, which is a big advantage. There are disadvantages of this, of course, because now you have an amplifier, there are linearity limitations, lots and lots of disadvantages. But the fact that it's input matched can be quite important depending on what's driving it. So right after the amplifier, what do? Well, we, of course, hit a mixer. And right away, it should be fairly obvious how this works now, because it's going to use frequency translation techniques and take advantage of a fixed filter in order to do your filtering. So let's talk about that. So the input goes in, gets amplified, goes into an up conversion mixer. This mixer has an LO frequency going into it, which we can adjust. So the entire frequency content of 20 megahertz to 1 gigahertz gets up converted by some carrier frequency. So it's shifted up in frequency. And then after that, it's passed through this cavity filter. So this microwave filter is built almost exactly the same way as the filters we looked at. You can see it does have a hairpin structures in the middle, and it does have cavity in the middle. Now this is not very wide, and this is most likely an evanescent mode filter. So we have capacitive, inductive, capacitive, inductive, capacitive, inductive structures in there. There are 4 of these capacitors, which are tunable with these screws, and I'll show you how those are tuned. So you can tune this and set it and fix it in frequency. So they don't tune the filter at all. What they tune is the LO frequency of these mixers. So by up converting it up, they place these somewhere in the middle of the band, and then they down convert using this other mixer here, and that's what they feed back into the output. So they keep the filter fixed, they tune the LO. Now there are obviously lots of disadvantages with that. Let's flick to the other side. Now, first of all, here's our LO coming in. That's why there's a Wilkinson divider in the middle. So it splits the LO into the left and the right side. These are coherent now and exactly the same frequency. So it doesn't really matter. This will never have a frequency translation at the end because the up and down conversion frequencies are identical. So this one goes and up converts and this one goes back and down converts. So what you end up with is exactly the same frequency content in terms of absolute frequency at the output. Now, there's a couple of other interesting points to this. This does not have a full PLL. In fact, the VCO they use, this voltage tune oscillator, is unlocked. Now, it has some disadvantages from the fact that it is unlocked because it can drift with temperature. And in fact, it does, and I'll show you that. But its absolute frequency doesn't really matter in terms of frequency conversion because you're using the same LO to up and down convert. So the input does not experience a frequency shift. But the center frequency will go left and right because this LO is free running in a way. But this is actually surprisingly stable. We'll take a look at this data sheet at the same time. So once it does that, then goes through here. There's probably some additional filtering and so on underneath. There's no point removing that. And then it comes out of this side. You can see the cable is tapped right over here. And the location in which you tap it in here really does matter in terms of the filter response. And I can go ahead and tune this. And I did play around with these screws to tune this exactly at the right frequency. So this is how the filtering is accomplished. So I have an enlarged version of what's in one of these. So you have a copper tube that's grounded on one side to this side, and then you have a screw that's grounded on the other side to the body. So they're both grounded. They normally fill this with some dielectric material. And then depending on how far you push the screw in here, you change the total capacitance because the overlap of these two regions gives you the total capacitance. Yeah, so that's it. This is a tunable capacitor. And by putting the appropriate dielectric in here, you can take advantage of increasing the capacitance per unit area so you have a wider tuning range. And that's exactly what these screws are. If I tilt this to the corner here, like so, you can see you might be able to barely see that there is a dielectric material in those copper lines. It's a fairly rough, it's obviously handmade. But yeah, so an evanescent mode filter, fixed in center frequency, tunable VCO, 2 mixers, and that's your filter. So you can see a very different architecture than everything else we've seen so far. Now, so what is the center frequency of this? Can we find out? Well, yeah, by measuring it, we can find out because we can measure the frequency here. We have exposed traces. We can catch what frequency that is. We can set this to a center frequency that we want, and we can find out exactly what the center frequency of this bandpass filter is. And that's why they can get a constant bandwidth because the bandwidth is determined only by this, and this is fixed. And that's the clever part of this design. At the same time, this can be extremely nonlinear because you have amplifiers and mixers, up and down mixers and everything. So this can have a pretty nonlinear response. So I do want to stress test it and measure it. So now let's go and do a whole bunch of measurement on this and really understand it. And by the way, if you were wondering what this is, this voltage tune oscillator has a tuning range of about 20 volts. So they need to create some higher voltages to tune this above the power supply coming in. And this is a DC-DC converter based on capacitive mode switching, and it brings that voltage up. There's no power consumption on the tuning voltage, so this doesn't need to provide a lot of current, but it does need to be able to go above the power supply voltage. And they do this with this op-amp here, which is connected to the external potentiometer and this DC-DC converter. Yeah, pretty nice. Very simple design in a sense, but it does work. It does give you some unique properties. And before I forget, 2 additional points. I mentioned that it is shielded at the output more than at the input, and that's because here everything is already filtered. So this coax line that comes over here and goes in here, anything that couples into this port is essentially bypassing the filter. So it's important to get rid of it. This thing is broad spectrum. So it goes from 20 megahertz to 1 gigahertz, and it fills this potentially with some EM radiation, and they want to block it, make sure none of it goes over here. Because if it jumps from here to here, then it defeats the entire filtering. That's why this has additional shielding. And then you also may be surprised that one end of this is open. You know, why are stuff not leaking out this way? That's because there's nothing for this pin over here to couple into. It couples into the evanescent mode between these 2 sections. So it's like an LC circuit, right? You have a C and an L and a C and an L. There is no L on this side. So of course the signal is going to go this way and not this way. And of course that's under ideal condition. Some things will leak a little bit out of this. That's why I'm surprised why they didn't close this side. You can see that they've closed this side, and I put some additional tape on it just to make it a little bit better. But this is close to the output. So they really want to take precaution to close this. But they didn't do it on this side. There is some disadvantage in closing this because you get a bit of additional capacitance coupling to this one in the middle, and that can detune it anyway. So they haven't done that. I'm not sure exactly why, maybe just because of room There's no room to put this something here. But anyway, I'm going to leave it alone. I'm not going to play around with it too much. I already tuned it by adjusting these capacitors and made the filter absolutely perfect, because when I got it, it was completely detuned for whatever reason. And another problem I found is that this was disconnected. The soldering was really rough and it had essentially broken off, so nothing was working. This had many problems, partially probably because it was assembled in not the greatest way. So anyway, it's now, I think, fully repaired, so we should be able to measure it. So now let's move to Rohde-Schwarz instruments in order to measure the frequency response of this tunable filter and figure out what the center frequency of that fixed microwave filter actually is. So we're going to use three instruments. At the bottom I have the NGM202 dual power supply from Rohde-Schwarz. I'm applying 18 volts, so you can see that this thing consumes about 218 milliamps. So it's not very high, of course, but it is nonetheless something that burns power. We'll look at some of the properties of the circuit and its stability as well. Now I'm going to use two spectrum analyzer and network analyzer hybrid instruments, so we can simultaneously look at the VCO frequency and look at the S parameters of our filter, and that's the ZNL6 and ZNLE6. All of these instruments have had extensive teardown and reviews here on my channel that you can find. So here's our instrument over here. I have a probe like this that we can look around, so we can figure out what the carrier frequency of the VCO is. Everything is running right now. We'll close it up eventually. Now, one thing to keep in mind is that I do have a 20 dB attenuator at the input. That's because I want to make sure that this is really running in linear mode. So whatever number we read on the S parameters, you have to add 20 dB to it. That's the actual gain of the circuit. There's a 20 dB attenuation. Let's take a look. Okay, so right off the bat, we see some interesting properties. So at the bottom, S21 is the forward response of the filter. And if you look at S12, we have absolutely nothing. And that's because, of course, this is not bidirectional. This only works in one way. Now, we also see the bandpass filter right over here. I'm going to adjust it and bring it right on top of a marker. Okay, you can see the entire shape of everything changes. Remember, the entire frequency is up converted. It is very narrow band, which is quite nice. Let me see if I can hit exactly 500 megahertz. Oh, it's very sensitive. See, you can hit that peak. There you go, almost there. There it is, roughly around here. So this thing actually has quite a bit of gain, because we're reading about 10 dB over here, and there's a 20 dB attenuator in front of it. So this thing has a 30 dB gain. So it's more than just a filter, it's also an amplifier. Now this gain can hurt you, and we will see it when we measure its linearity. But it is extremely sharp. Now if I move this across frequency, you can see that its relative bandwidth stays constant. So it does have a continuously shrinking fractional bandwidth, but it does have a constant bandwidth. So I also want to zoom in there so we can take a look at the shape of the filter and really ensure that indeed it does have a 4 megahertz band. But look at how sharp that is. And yeah, 30 dB of gain is a lot of gain. Alright, so here's a zoomed view. We are looking from 490 megahertz to 510 megahertz, and here's the shape of the filter response. We have 30 dB of gain, and look how narrow band this is, and this stays constant throughout the entire frequency tuning, of course. So it does indeed have the 4 megahertz bandpass filter as promised. Now all I'm going to do is I'm just going to blow onto the board, and just with that you can see how sensitive it is, because there is no PLL. Everything is free running. Take a look. See, that's all I did, and it already shifted by a couple of megahertz. Now of course it's not in an enclosure right now, but this thing is definitely extremely sensitive to temperature for its center frequency, but it does not do a frequency shift, as I already explained why. So now let's take a look at the above and figure out what is the center frequency of that filter. So I have placed the probe on top of the printed circuit board over here where the Wilkinson divider is, and you can see a strong tone coming out, and that tone is at 1.795 gigahertz. Now if I change the tuning frequency of the filter, you see what happens? That moves around with it, right? So that makes sense, because we're tuning the LO of those mixers in order to place it within the appropriate area where we want to filter it. So I'm going to tune this exactly to the 500 megahertz again, keep it around the 500 megahertz. And this means that if the VCO frequency is 1.7 gigahertz or 1.8 gigahertz, and this is at 500, that means that microwave filter must be at 1.3 gigahertz fixed. So that's what they do. They up convert just above the maximum frequency, filter with a microwave filter, down convert back, and that filter is a fixed 1.3 gigahertz, 4 megahertz bandwidth microwave cavity filter. And that's how this whole thing works, which is quite interesting. Now for our next experiment, let's move on to Tektronix. I'll be using the 6 series mixed signal oscilloscope. This is an 8-channel revision B. Fantastic oscilloscope. I've done a full review and teardown of it. You should definitely check out. And on the left here, I have the Tabor Electronics quad-channel 12 gigahertz synthesizer. Now we're not going to use this to 12 gigahertz, of course, but it gives us 4 independent CW sources. I'm combining that into a power combiner, passing that into a coupler. The coupled path goes into our filter, and the straight path goes into the oscilloscope. So what this allows us to do is to look at the input of the filter here and the output of the filter here. And we can tune the filter and see the effect. And we're going to generate 4 tones over here that we're going to take a look at the same time. So this allows us to do a lot of things, but in particular, I want to show you the impact of the linearity of an active filter like this and what are some of its disadvantages. Let's give it a try. I'm always really impressed with the capability of the GUI and just the general oscilloscope here that we have from Tech. They've done a really great job making this easy to use, especially with the DDC function, the digital down conversion. So here we have channel 1, that's the input to our filter. And here's channel 5, that's the output of the filter. And then we have the spectrum view of both of those inputs as well, from 0 Hz to 1 GHz, which is the range of the filter. So if you look, you can see that I have 4 tones coming into the filter, 500, 600, 700, and 800 megahertz. They're exactly the same amplitude, minus 27.5 dBm, and they have a randomized phase. And that's why you can see at the bottom here, the time domain signal. The time domain signal is not that interesting because there's 4 sinusoids essentially superimposed. Now at the output, we see almost nothing. These little tiny tones that you see here are actually from the oscilloscope. That's because I haven't ran the signal path compensation, which you can run on this to get rid of that. I haven't run it for a long time. That's probably why they're still there. But anyway, it takes about an hour to run that. So if you look, there's nothing there. But if you look very carefully, you see a little tiny thing here. If I move the center frequency, you can see that moves around. I'll talk about this, right? So that's because this filter has gain. So that gain means that there's going to be some additional noise at the output, and you can use that to figure out the noise figure of this. I have a complete noise figure tutorial that I'm making that's going to make all of this much more clear. You'll learn about Y-factor methods and other means of measuring noise figure. But yeah, that's the center frequency. Moving around is very narrow because it's only 4 megahertz, and as soon as I approach the first tone, you can see that the filter will allow the first tone to come through, and then it's going to reject it. We continue on. Here's the second tone, it's going to reject it. Here's the third tone. And finally, here's the 4th tone, right? So it's exactly what you would expect it to do. So let's leave it here, I don't know, on this one. Let's maximize it so we're really in the middle of the band there. There it is. So it's putting at minus 7 dBm. Remember, we're putting actually minus 37 because there is another 10 dB attenuation. So it does have the 30 dB gain exactly as we anticipate. So now all I'm going to do is I'm going to increase the amplitude of one of the out-of-band tones. Not the one we're looking at, but let's say the one at the beginning. Now this one should be filtered by our filter, of course. But remember that there are amplifiers and mixers before we hit the first microwave filter. All of those guys have to see all of these tones at the same time. So their dynamic range is determined by the sum of all of these signals, not by the individual one, because that's before the filter. And that's a primary disadvantage of an architecture like this. Let's go ahead and increase this one. So I'm going to increase it. There you go, making it larger and larger and larger. Nothing's happening so far. I'm going to change the scale here twice. There we go. Let's keep going. Now keep an eye on this one. Right? It's still at minus 7. We're at minus 17, 16 dBm at the input. Keep going. 10 dBm. And look at that. This is getting smaller and smaller, and there's some spurious tone appearing near the edges, which is not part of the signal. So now I'm putting about 1 dBm, so you have to subtract 10, so it's about minus 11 dBm, and we've already corrupted the signal we're looking at. We've reduced this amplitude by 7 dBm, and we've introduced 2 tiny tones near it. So that, of course, is because you can see that those other tones move with the filter, so they're indeed from the filter. Those are mixing terms from the LO feed through, from the individual tones, and everything adding up. So this filter is now officially, essentially broken because of the fact that we are saturating the input. And that's a disadvantage. But of course, you wouldn't know this if you're only looking at the output, because you wouldn't know that these are present. So in the presence of a strong blocker signal, this filter will no longer work. So keep in mind that the majority of the other filters I showed you, especially the passive microwave ones, do not have this problem. What they do instead is that they reflect this signal back out of the filter. So if you have a driver that does this, you could cause nonlinearity on the driver's side. But the filter itself is essentially completely linear, within reason, of course. And there you have it. I hope you enjoyed this tutorial style video once we dug really into the architecture of this and compared it with other circuits. As always, thanks to the Patreon support for making these possible. Do check out the Patreon page if you enjoy this kind of content. I'll try to do more of these tutorials. And for the noise figure, I have another video coming out, so we're going to take a look at the noise figure on this one separately. There's a lot to talk about noise figure as well. As always, I'll see you in the comment section.